Let's study 10th standard ICSE Physics, Chapter 1A, Sums of Moment of Force. Physics, exercise 1A, numericals. Cancel the first one, it's very easy. Let's do the third one. The force is of 2 newtons. It will rotate this clockwise. We have to calculate the moment of force about the center O. So O is the pivot. The diameter is 2 meters. So the perpendicular distance between the point of application of the force and the pivot is the radius, which is 1 meter. And the moment of force formula is F into D, that's 2 into 1, 2 Newton meter clockwise. You should also mention the direction of rotation in every answer. And Roman number 2 is about point A. Now here, the diameter is the total distance. That's 2 meters. So now the moment of force is 4 Newton meter clockwise. Next question, 4.1. What is the moment of force about O for F1? That will be 5 into 2. And moment of force F2 about O is 3 into 4. And what's the total moment of force? So that will be the net torque or the net moment of force. That's always the anti-clockwise moment minus the clockwise moment. So by convention, we consider the clockwise moment as negative. So here, the clockwise moment is greater than the anti-clockwise moment. So the net moment of force or the total moment of force or the net torque is 2 Newton meter clockwise, since clockwise was greater than anti-clockwise. Another way to solve this would have been 10 minus 12. Answer would have been minus 2 Newton meter. But in the end, we would have still written 2 Newton meter clockwise because negative simply means clockwise. Next, the 6th question. So we've got 2 forces, equal and opposite, parallel to each other and not along the same straight line. So they are a couple. Calculate the resultant moment of 2 forces about point A. Now one way of doing this is calculate the moment of force A and the moment of force B and add them up. A shorter way would be to use the formula of moment of couple, which is any one force into the total distance between the 2 forces, the perpendicular distance. So instead of using the distance from the pivot, we are using the perpendicular distance between the 2 forces. So we get the answer directly. It's 10 Newton into 0.5 meter, which is the total perpendicular distance. So the answer is 5 Newton meter. And why this method is easy? Because no matter where the pivot is, the answer will be same. So Roman number 2, Roman number 3 answers are also same, 5 Newton meter clockwise, because it doesn't matter where the pivot is. What matters is the total distance between the 2 forces. Hence we get the same answer, 5 Newton meter clockwise. Next, the 8th sum. A uniform meter rule. Meter rule means that the rule or the ruler is of 100 centimeter length. It is pivoted at its midpoint and a weight is suspended at one end. Where should a weight of 100 GF be suspended to keep the rule horizontal? That means to bring it in equilibrium. So first we have to draw the diagram. Here you can see I am assuming 0 centimeters to be on the left hand side and 100 centimeters on the right hand side. The pivot is at the center, which is 50 centimeter mark. They said hang 50 GF at one end. Done. And using 100 GF, we have to bring it back to equilibrium. You see, if there is only 50 GF moment of force, then it will tilt anti-clockwise. That is, this ruler will tilt to the left. So to bring it back to equilibrium, we'll have to use a 100 GF weight. 100 GF weight, but where should we keep it? Well, let's assume that we have kept it at a distance of x from the fulcrum on the other side. Obviously, we won't keep this weight on the same side. Then it will tilt even further. We want to bring it back into equilibrium. So we write the assumption here. And then we know that in equilibrium, the total anti-clockwise moment is equal to the total clockwise moment. That is the principle of moments. That means 50 into 50, because distance is 50, is equal to 100 into x. Remember, the distance is always calculated from the fulcrum. So after solving this, we get the value of x as 25 centimeters. So don't forget to write the final statement. That is, at a distance of 25 centimeters from the fulcrum on the other side. Next, the 9th sum. Again, a uniform meter rule, that's of 100 centimeters, but this time it balances horizontally on a knife edge at 58 centimeters mark, so not the midpoint, when a weight of 20 GF is suspended from one end. Mark the sum as IMP. So here, if the pivot is at 58 centimeters, remember, the weight of the ruler always acts at its center of gravity, which will be its midpoint, 50 centimeters. So in this case, the weight of the ruler also comes into the picture. So let's call it x gram. That is, the force will be xgf due to the weight of the ruler. And it will be anti-clockwise because the fulcrum is to its right. In the previous sum, there was a weight of the ruler acting at 50, but since it was passing through the fulcrum, it provided neither clockwise nor anti-clockwise moment. So it was irrelevant for our calculations. But here, it will be relevant. The ruler will tilt towards the left. But to bring it back to equilibrium, we have put an additional weight of 20 GF at the other end, at the edge, 100 centimeter. So now, in equilibrium, the total clockwise moment and anti-clockwise moments will be equal. So Roman number 1, they've asked us to draw the diagram. So this is the perfect diagram. And Roman number 2, we start solving. Always the assumption statement of x in equilibrium, total anti-clockwise moment to be written on the LHS and total clockwise moment on the RHS. And then substitute the values. So x into 8. Yes, the distance from the fulcrum is 8. Remember that. And what's the distance from the fulcrum out here? It's 42. So on substituting these values, we get the value of the weight of the rule as 105 GF. So to balance it, 20 GF was sufficient. How is that possible? Well, that's because here the distance was less and the distance was more. So ultimately the torque left hand side and right hand side were equal. And the net torque is 0 and hence it is in equilibrium. It is balanced. Next, question 11. A diagram is given. First they've asked, will this be in equilibrium? Well, if you look at the anti-clockwise moment, it is 40 into 40, that's 1600 GF centimeter. And on the right hand side, that is clockwise, we have 20 into 40, that is 800 GF centimeter. So it will not be in equilibrium. Then they ask, in which direction will the rule turn? Obviously it will tilt clockwise, anti-clockwise, because that is greater, the left hand side. Second question, how can the rule be brought in equilibrium by using an additional weight of 40 GF? So first of all, think and tell me, where would you put this additional weight, on the left hand side or right hand side? Well, you would definitely put it on the right hand side. So after solving Roman number 1 like this, we'll draw a diagram for Roman number 2. Notice that I have not put the equal to sign here between anti-clockwise and clockwise moment. Don't do that. Instead, draw a line because initially they were not equal. If they were equal, it would have already been in equilibrium, but they are not in equilibrium. It will tilt anti-clockwise. Now that we've put an additional weight of 40 GF at some distance x from the fulcrum on the right hand side, it will now be in equilibrium. That was the whole aim of adding this. And when it is in equilibrium, the total anti-clockwise moment will be equal to total clockwise moment. That means 1600 is equal to 800 plus 40x, because 40 into x is the new moment we have added. And now solve this and get the value of x like this. Don't forget to write the final statement by placing the additional weight at 70 centimeter mark. That's right. If the new weight is to be added 20 centimeters to the right, it is at the 70 centimeter mark. Yeah, we could have also written 20 centimeters to the right of the fulcrum. Such a statement would also be allowed. Now the 14th sum, again an IMP sum. The diagram is given. Roman number 1, calculate the total anti-clockwise moment about O. See, I've jumped to this Roman number 1, but you should always pause the video and read the whole question first. Understand the question, then only see the solution. The total anti-clockwise moment is 150 into 40, that's 6000 GF centimeter, that's easy. And Roman number 2, the total clockwise moment will be 250 into 20, that's 5000 GF centimeter. So Roman number 3, what's the difference? Yes, there is a difference, they are not equal, it is not in equilibrium. It's 6000 minus 5000, which is 1000 GF centimeter. Anti-clockwise, we have to mention the direction of the excess, like this, anti-clockwise. So Roman number 4 now, what distance from O should we keep 100 GF weight to balance the meter rule, that is bring it back to equilibrium? So again, we will obviously put it on the right hand side because the left hand side moment was greater. Hey, but the weight of 150 GF is less than 250 GF. Yeah, but we are talking about the moment of force, not just the force. Here the distance is greater, so the product is greater. So let's keep 100 GF at a distance of, let's say, x centimeter to the right of the fulcrum. So now the total anti-clockwise moment will be equal to total clockwise moment, and you solve it and get the value of x, which becomes 10 centimeters. So 10 centimeters on the right of the fulcrum. So somewhere around here. But while drawing the diagram, I had no idea what will be the value of x. So I drew it out here far away. That's okay, that doesn't matter. The final answer should be written as a statement. Next, the 15th question. a uniform meter rule of weight 10 GF is pivoted at its 0 mark. Roman number 1, what moment of force depresses the rule and how can it be made horizontal by applying the least force? So initially we draw a diagram with the fulcrum at 0, and obviously the weight of the ruler of 10 GF will be acting at its midpoint like this. So this will provide a clockwise moment. Ignore this for a moment, the black force. Initially we just had 10 GF force acting. There was no anti-clockwise moment balancing it. So the ruler would tilt to the right. If you try to balance a ruler at its 0 mark like this, it is tilting towards the right because of the clockwise moment provided by its own weight. So to bring it in equilibrium, what I would do is I would apply a force in the upward direction at its outer edge. That way I will have to apply the least force. If I apply here, then also it can be raised, but I'll have to apply a greater force to bring it back to equilibrium. So that's the question. So first of all, the moment of force which depresses the rule was the weight of the rule, which is 500 GF centimeter, clockwise, clearly. And in order to bring it back to equilibrium, let's apply a force of x GF at the 100 centimeter mark. So you have to mention that statement. And now in equilibrium, total anti-clockwise is equal to total clockwise. This is the clockwise moment, that is 10 into 50. And this is the anti-clockwise moment, if you notice, that is x into 100. Yes, the total distance is 100. So substitute the values and solve, and then you get the answer as 5. So by applying force of 5 GF upwards at the 100 centimeter mark. That's how we write the final answer. And now the 17th question, which is also IMP. A uniform meter rule of mass 100 gram is balanced on a fulcrum at mark 40 centimeters by suspending an unknown mass m at the mark 20 centimeters. So first of all, find the value of m. So let's draw a diagram for this. Drawing the correct diagram is very crucial. So we have mass, unknown mass m at 20, 100 GF at 50, fulcrum is at 40, they are in equilibrium. So the equation, substitute the values, and we get the value of m as 50 gram. Yep, make sure you write gram and not GF because they've asked for the mass, not the weight. Now Roman number 2, to which side will the rule tilt if the mass is moved to the 10 centimeter mark? So right now it is in equilibrium. What if we shift this mass m to the left at the 10 centimeter mark? Will they be in equilibrium any longer? No, they won't, because we have increased the distance here. Earlier the distance was 20, now the distance will become 30. Here the distance is 10, by the way. So the answer is it will tilt on the side of m. I'm not going to write on the left side because the diagram was not given. So I have assumed 0 to be on the left side. So a better way to write the answer would be on the side of m. Roman number 3 is, what is the resultant moment now? So resultant moment is always anti-clockwise minus clockwise. What is anti-clockwise? 50 into 30. And clockwise is still the same, 100 into 10. So there is an excess torque of 500 GF centimeter anti-clockwise. That means it will tilt like this, anti-clockwise. And the fourth question is, so where should the weight of 50 GF be suspended so that it comes back to its equilibrium position? So we'll draw another arrow out here, a 50 GF weight at a distance of x centimeter from the fulcrum on the right hand side, that is on the other side. So now it will be in equilibrium. So the total anti-clockwise moment, the new one, is 1500, and the total clockwise moment is the 1000 originally plus 50 into x. Substitute, solve, and you get x as 10. That means we have to suspend that weight 10 centimeters to the right of 40, which is at the 50 centimeters mark. So that's why I wrote at the 50 centimeters mark. Yeah, it's coinciding with this, interestingly, even though in the diagram I didn't draw it coinciding because I didn't know that x would come out to be 10. So that's how we write the final statement.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.